So, hello everyone. My name is Rohit Kal, and this is live session 5. So, in the last class, we have started discussing about linear algebra, and this week we will continue with that. So, first, we will deal with the LU decomposition. So, so here is a example problem. Just a second. Yeah. So, here this is the first problem. So you need to find L and U for that. So given here your matrix is this is your matrix, so you need to perform the Gaussian elimination, and you need to store the conversion matrix for that, so to get L. So now here the first stage will be your first stage will be now R2 to convert it to R2 plus R1 by 2. So this will be so this is your first step, and the matrix will be 4 3 minus 1, and it will be 0. So R2 plus R1 by 2. So R1 by so this will be minus 4 plus 3 by 2. So minus 4 plus 3 by 2 minus 8. So it is minus 5 by 2, and it is 5 minus half. 5 minus half is equal to 9 by 2. So this will be a 9 by 2, and minus 1 to 6. Now, what matrix gives this say this matrix? So the conversion matrix we can write as E21. This will be equal to 1 0 0, because we are not changing row 1. Now the second one will be, so we are multiplying row 1 by half, and we are adding with row 2. So half 1 0 0 0 1. So you can verify it. So let's verify just for once. So it will be 1 0 0 half 1 0 0 0 1. So this into matrix A, 4 3 minus 1 minus 2 minus 4 5 minus 1 2 6. So resultant matrix will be, so it will be same, 4 first row first column 4, first row second column 3 minus 1. The first row will remain same. This is half into 4, the second row first column. Half into 4 is 2 minus 2 0. It will say this is 0. So this is 3 by 2 minus 4. 3 by 2 minus 4 is 3 by 2 minus 4 is minus 5 by 2, and minus half plus 5, this is 9 by 2, and the last row will remain the same, minus 1 2 6. So this matrix is the correct one. Okay. Now, now is the alternate question. What matrix will give back this matrix? So that matrix will be E21 inverse. Okay, and E21 inverse, you just need to put a minus half over there. We can again verify that. So let's verify. Just delete it. Okay, so the claim is, when I put half, this will give me E21, because it is operating on the row, this first two rows. So that is the E21. Now E2 inverse, if I multiply E2 inverse with this matrix, then we should get our A back. Okay. So so now the claim is, so previously we are adding row, we are multiplying. So previously we are multiplying row 1 by half and adding with row 2. Now what will be the opposite process? The opposite process will be, we are multiplying the row 1 by minus half and adding with row 2. Okay, just verify with it. Let's verify. This is E21 inverse, and if I multiply with this matrix 4 3 minus 1 0 minus 5 by 2 9 by 2 minus 1 2 6. Let's verify it. So here the first row will remain the same. Now minus half. So minus half plus, so minus half times minus 4 is minus 2. Okay. So I am just multiplying this. Then minus 3 by 2 minus 5 by 2 is minus 4, plus half plus 9 by 2 is 5, and this yeah, so this is the matrix, and the third row will remain the same, minus 1 to 6. So this claim is correct. Okay. So if e21 is this, then e2 inverse will just we need to change this sign. We will keep the identity matrix intact. Identity matrix means this one intact, 1 0 0 0 1 0 0 0 1 form intact. We will just change this extra term. We will just change the sign of this extra term, and we will get our e21 inverse. We will need this e21 inverse at the end. Okay, so let me just erase this. I will. So we need this e21 inverse. So okay, no, no, this. So we will need this e21 inverse. So I will store it for now. Now I will move to the second step, which is I will now I will now operate on row 1 and row 3. Okay. So again observe this matrix A. So what will be the so what will be the step? So that's the next step will be this R3 plus R1 by 4. If we do this, you can see that this element will be 0. So let's solve that problem. So let's solve this. So it will be 4, 3 minus 1. So this is my modified second row, like 2. Now, so now I am multiplying row 1 with 1 by 4 and adding with row 3. So it will be, first row will be 0, then 2 plus 3 by 4. What is 2 plus 3 by 4? 2 plus 3 by 4. So it is 9 by 4. Okay. And minus 1 by 4 plus 6. So 6 minus 1 by 4 is 25 by 4, right? It's 23 by 4. I hope I am not making any mistake. So yeah, so again, so multiply this with 1 by 4, multiply this with 1 by 4, so it will be 1, so it was with 0, then 2 plus 3 by 4, 2 plus 3 by 4 is 4, 8, so it will be, sorry, this will be 11 by 4, and it will be 6 minus 1 by 4, so it is 23 by 4. Okay. And the corresponding matrix E31 will be just similar to this one, just similar to this one. Their half will not be there, so it will be 1 0 0, because we are not doing this, because row will kept intact. The second row will also kept intact, that is 0 1 0, and the third row will be so I am multiplying first row with 1 by 4, so this is 1 by 4 will come here, then the second row will this thing will not change, then it is 1. Okay. So this is the third row. So I am multiplying first row with 1 by 4 and adding with third row. So this is the physical meaning of them. Similarly, E31 inverse will be minus 1 by 4 0 1. In the place of 1 by 4, just need to put minus 1 by 4. Now the next step. So this is now this is our so far. This is our resultant matrix so far. Okay. Now there is another. So now this is the pivot element, and I need to operate on this. So let's do the operation. So now this is a little bit tricky. So R3. So this is 11 by 4. So I need to multiply with this something so that we get minus 11 by 4, and we will just add it. So what will be the factor? Maybe 4. 2 into half by 4 into 11 by 5. So the 11 by 10 is the factor, right? 11 by 10 is 4. Yeah. So 11 by 10 is the factor. Plus 11 by 10 are 2. So this is the new step. So it is more 3 minus 1, 0 minus 5 by 2, 9 by 2, 0. So I am multiplying the 11 by 10, so it will be 50 minus 55 by 20. So if I divide it by, so it will be minus 11, so it will be 0. So 9 by, so the new step will be 9 by 2 into 11 by 10 plus 23 by 4. So this will be the last element. So let's calculate it. So it will be 99 by 20 plus 23 by 4. So if I multiply it by 5, it will be 115. So it will be 115 plus 99 by 20. So what will be the value for that? 115 plus 99 by 20. So this value will be 10.7. Okay, so this value will be 10.7. And now what will be the corresponding E32? So I will remove this rough. So if you do this, you will get this matrix, and this is your U. You see that this is a upper triangular matrix where the where the elements below the diagonal is 0. Now what will be the corresponding E32? E32 will be I have, so first row will be same. Second row will also kept intact, but I am changing that third row. Third row I am changing. I am multiplying the second row with 11 by 10 and adding with the third row. So 100 010 011 by 10 1. Okay. So I don't have any space here, so I am writing over writing. So I am writing here. So so how can we write this complete matrix, the complete transformation? The complete operation we can write in this fashion. So E32, E31, E21 A is equal to U, because at the end I am getting this U matrix. This is my final matrix. This is my final form, and these are the operations that I have performed. So the whole row transformation, this row exchange operation, those Gaussian elimination operation are contained in these three matrices. So now what will be the, L? So L matrix will be A equal to E32, E31, E21 inverse U, and this will be E21 inverse, E31 inverse, E32 inverse U. And we already know what is E21, E31 and E32, and E21 inverse will be just minus up over here, E31 will be minus 1 by 4 here, and E32 will be minus 11 by 10. Okay, so now if you so we know these values. Now you just need to do a simple multiplication process, and in the resultant will find you will get L. Okay, so this is the this is the technique to solve the LU decomposition using the Gaussian elimination technique. So now, so I hope this is clear to you. So now let's move to the second question. So this is an MCQ type question. So it says that for find a correct statement that for a symmetric matrix A, all eigenvalues are real, all eigenvalues are imaginary, they have repeated values, or none, and none of this. Okay. So now we know that it was discussed in the class that for a symmetric matrix case, all the eigenvalues will be real. Okay. So the option A is the correct answer. Okay. Now, so now you are given a matrix L. Now using Cholesky's method, you need to find what will be the matrix A. Okay, and what was the method? A equal to L transpose. Now when this is satisfied, this is satisfied when it is positive definite, and you can see, you can find the positive definiteness from this pivot element. Both of them are greater than 0, so it is a positive definite matrix. Okay, so this is the technique, L in L transpose. So you just need to find the transpose of this matrix. Now remember that this is a complex matrix. Okay, this is not a real matrix. So L equal to 1 0 1 minus 5i 2. Now what will be the L transpose? L transpose will be L bar of its conjugate. Okay, so it will be 1 1 plus 5i 0 2. Yes, yes. So it will be, so this will be so this will be the transpose. In case of real matrix, you just you can just shift this, but for the imaginary case, you automatically have to calculate the complex conjugate of it. Okay, so now multiply L and L transpose. So it will be 1 0 1 minus 5y 2 1 1 plus 5y 0 2. So this will be 1. Plus 5y, 1 minus 5y, and the third one will be 1 plus 5 square by 4. So it will be 25, 26, 30. So the matrix will be 1, 1 plus 5y, 1 minus 5y, and 30. This term will come from this term will appear from the second row and second column. 1 minus 5y, 1 plus 5y is equal to 1 plus 5 square and plus 2 square. So the final result is 30. So this is your matrix using Cholesky's method. Now this is the so now this is so here now in the case you have to just do the opposite. Here your A is given. Now using Cholesky's method you need to calculate what is L22 and L11. That means the L11 0, L21, L22, the lower triangular matrix, you need to calculate these two elements. Alright, so again A equal to L transpose. Okay, here this is the L11 0, L21, L22. Now you see that this is also an imaginary matrix. Okay, so the transpose L21, this will be the bar L21 0 22, because the L21 can be an imaginary number, so I am taking the complex conjugate. If it is a real number, then it's no problem. So 1 plus 5y, its complex conjugate is 1 minus 5y, and complex conjugate of 2 is the 2, the real value. There is no problem in taking the complex conjugate. So now I need to calculate L11 and L22. So first let's calculate L11 square. So from the matrix given, L11 square equal to 9. So I can take L11 equal to 3. I am taking the positive value. And for the L22, so what will be the, how can we find L22? L22 will be L21 square, L21 bar plus L22 square. Okay, this is equal to 25. Now L2 to L21 bar equal to the absolute value plus L22 square equal to 25. Now I still am not, so I don't have the value of L21, so I need to calculate that. So how to find it? So from this first row and second column calculation, so it will be L11 L21 bar. This is equal to your 12i. Right. Now your L11 is 3. That means L21 bar equal to 4i. So here you just need the magnitude of it. So modulus of L21 is equal to 4, right? So its square is 9. So its square is 16. It is going there. So L22 is equal to again 3. So what is your L11? You are getting L11 equal to 3 from here, and from here you are getting L22 is equal to 3 as well. So this is your solution. Okay. So the next method. So this is the complete calculation. Now, again a problem on positive semi-definite matrix. Okay. So this is your so these are two matrices, A and B. So here A is 1, 2, 3, 4, 5. A is a 2 cross 5 matrix, hmm, and B is 1, 2, 3, 4, 2 cross 4 matrix. Okay, so these two are rectangular matrices. Okay. Now, how to find the positive definite if this how to find if this matrices are positive definite or not? So here you can you cannot calculate the eigenvalues because we only know because we know the mechanism of calculating eigenvalues from for a square matrix only. But but it was which was discussed in class that for a positive definite matrix we can find it from the element itself. If the both of the pivot elements are greater than zero, then this matrix we can say that it is positive definite. I mean, not both of the pivot elements. If all the pivot elements are greater than zero, we can say that this matrix is positive definite matrix. Now see these two matrices. Okay, so clearly this is a pivot element. Clearly, this first element is a pivot element. Fine. Now, what will be the second pivot element? Okay, so second pivot element will appear at the new row. Now, these first three elements they are zero. So they can the zero we do not consider as a pivot element. This is the second pivot element. This is the obvious choice because this is the first non-zero number appear after three zeros. So here this is minus 3, this is 2. So both of them are not greater than 0. So this is we can say that this is not a positive definite matrix. But in case of B, this is one pivot element. This is greater than 0. This is another pivot element. So because this is the first 0, so this is the non-zero number. So this is the pivot element. So this is greater than 0. So both of the matrices, so both of the pivot elements are greater than 0. So this is a positive definite matrix. So here, let's look at the options that both B and A are positive definite. So this is not the correct one. Only A is positive definite. No. Only B is positive definite. Yeah. So option. Okay. So this will be the option C. So option C is the correct choice. All right. Now this is a small proof, but we will to find pivot to rectangular matrix. Okay. So this is not basically any rule actually. So uh, suppose anyway, so you just get the idea from the square matrix. Okay, suppose A B C 0 D E 0 0 G. So the obvious choice. So how do we get the pivot element? Okay, so this is one pivot. This is obviously the pivot element. Okay, this is another pivot element. Why? Because this is 0. The, each pivot elements appear as the new row. So this is 0. So this is 0. So I cannot take this as a pivot element. So this is the pivot element. Similarly, at the third row, this is 0. This is 0. But this is a pivot element. Okay. So if I write it in a different manner, okay. So suppose 0 D E 0 0 G A B C, you can see that we cannot do any operations on this. We need to do row exchange. Why we do that? Because I need a non-zero number at the beginning. That is pivot. Okay. So I need to change this matrix to this form. Then we can do some operations. Pivot is defined in that manner. So we just neglect 0 and try to find a nearest non-zero number. The same thing is happening for the non for the rectangular matrix as well. So this is the non-zero number. So this is a obvious choice for a pivot. But then we go to the next row, the new row. That we here we see that first three elements are zero. So we cannot take those as pivot element. Okay, and below that below that I don't have any other rows to exchange with it. So the obvious choice will be this number 2. The same thing happen here also. The first element is 0 in the second row, and the second element is 2. So this is the obvious choice for the pivot. So that's all. Now, uh, if A and B are individually positive definite matrix, then what is the correct answer? Now, what is the condition for the positive definiteness? This is x transpose A x is greater than 0. This is true because A is positive definite. Similarly, x transpose Bx is also greater than 0. Now, for a matrix A plus B, let's verify that x transpose A plus Bx equal to x transpose Ax plus x transpose Bx. Now, this is greater than 0, this is greater than 0. So, x transpose A plus B, x is greater than 0. So A plus B will be a positive definite matrix, but we cannot clearly say about the A minus B because there will be a minus sign. So we don't know if it will be greater than 0, the final expression. But obviously this thing will be greater than 0. So A plus B is positive definite. Okay. Now this next question. This is again also it is again a problem on the positive definiteness. So find out the values of C for which the matrix 2 minus 1 C minus 1 to minus 1 C minus 1 2 will be positive definite. Okay. So let me write down the matrix. 2 minus 1 C minus 1 2 minus 1 C minus 1 2. So this is the matrix. Now so So there are many ways to find the positive definiteness. All the eigenvalues are zero. All the eigenvalues are greater than zero. Pivot elements are greater than zero. This if this condition is satisfied. And another is to find we can find it from the determinant. In order to do that, first we need to check this matrix and find its determinant if it is greater than zero. And if this thing, the whole matrix, this because this is a 3 cross 3 matrix, I need to find if the value of this determinant is greater than 0. Okay. So first take a look at the small matrix 2 minus 1 minus 1 2. So it will be 4 minus 1 3. So this is 3, it is greater than 0. Fine. Now I just need to take care of the large matrix, that is the 3 cross 3 matrix. I need to find a determinant of that. So let's do that here. So it will be 2 into 4 minus 1 plus 1 into minus 2 plus c plus c into 1 minus 2c. It should be greater than 0. Okay. So let's calculate this number expression. So it is 6 minus 2 plus c minus 2c square is greater than 0. This implies I am writing, so I don't have space here, so I am writing it here. So 4 plus 2c minus 2c square is greater than 0. This implies c square minus c minus 2 is less than 0. And I am taking the negative on that right hand side, so it will be, so previously it was greater than, now it will be less than. This implies c plus 2, no, not c plus 2, c minus 2, C plus 1 is less than 0. So C less than 2 less than minus 1. So this is the range. Within this range, for any value of C, this matrix will be positive definite. Okay. Now take a look at those options. So one option is C equal to 0. Obviously, C equal to 0 lies, so C2 minus 1. C equal to 0 lies within this range. So this is a correct answer. C equal to 0.5 is also again a correct choice. C equal to 1, again a correct choice. But C equal to 3, it is beyond the range. Okay. So the correct answer will be A, B, and C. Okay. All right. Now let's move on to the next question. Again, you need to prove it. You need to prove that A transpose A is symmetric and positive definite matrix. Okay. The first proof. So let's first try to prove that A transpose A is a symmetric matrix. This is a simple one. Now, for any symmetric matrix, if Z is a matrix, any matrix n cross n matrix, it will be symmetric. So this is the definition of the of a symmetric matrix. That is Z transpose equal to Z. Okay. Now, to test if this matrix is symmetric, so we just need to do A transpose A transpose equal to now this is again AB transpose. Sorry, not, I shouldn't take A here. Suppose there are two matrices C D. There are two matrices C D transpose. The result is D transpose C transpose. Okay. Now this is A transpose A. A transpose A whole transpose. So it will be this one will come first. A of transpose into A transpose transpose. Now A transpose transpose is the same matrix, so it will be A transpose of A. So see that transpose of this matrix is giving this matrix back. So this matrix is a symmetric matrix. So the first option is proved. Now I need to prove that this is a positive definite matrix. So how to do that? So X transpose A transpose A X is greater than 0. I need to do that. Or the correct will be positive semi-definite. For semi-definite case, it will be greater than or equal to 0. Now, so it is, I can write it in this way: X transpose A transpose AX is greater than or equal to 0, right? So this is AX transpose AX is greater than 0. This is also true. This one is coming from this identity. X transpose A transpose equal to AX transpose. Now, now from the eigenvalue relation, AX equal to lambda x. So this implies lambda x transpose into lambda x. I should not write this greater than 0 right now because I am going to prove that. So equal to this equal to, now lambda is a scalar. Lambda is a constant value. So lambda transpose is lambda itself. So lambda x transpose lambda x. Now again, this is not a matrix. This is just a value. So I can push it here. Lambda square x transpose x. Now what is x transpose x? X transpose x is the two norm. This is the expression for the x transpose. So this is the value for the x transpose x. Now this term, now lambda square is greater than or equal to 0, obviously, and norm of x square is greater than or equal to 0. So this whole term x transpose I should write it here. So it proves that x transpose A transpose A x is greater than or equal to 0. Okay. So this matrix A transpose A is symmetric and positive definite, semi-definite. Okay. Now, all right. Now, now this is a new type of question. So a matrix is given to you, A equal to 2 minus 1 minus 1 2. This is a symmetric matrix. Yeah. Now you need to find the spectral radius for Gauss-Seidel and the Jacobi method. GS is the Gauss-Seidel method. Now, what is spectral radius? Spectral radius, as discussed in the class, spectral radius is the largest eigenvalue or corresponding to some matrix. Okay. Now, for the Jacobi method, first let's do the Jacobi method. Then I will solve the Gauss-Seidel method. Okay. I will not solve here completely. Later, I will show a code where I have calculated that. There you will be able to see the value. But now for the method, so here any matrix I can divide at L plus D plus U. Here D equal to, for this matrix, D equal to 2 0 0 2, L equal to 0 0 minus 1 0, U equal to 0 minus 1 0 0. Now I am trying to find the expression of X equal to P. So that means L plus D plus U X equal to B. Now, in case of the Jacobi method, what we do, Jacobi method is that I only the so what was the expression? It was xn plus one, suppose xj n plus one equal to some b of j minus a1 aj1 x1 n plus a j2 of x2 n dot dot plus dot 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 dot. So on the take home message is, so on the this will be the current step iteration. Everything on the right hand side is from the previous step. So I will take this idea. So and the below the and the bottom it will be a j j. Okay. So I will take this idea, and it will be dx equal to b minus L plus u x, right? This implies x equal to d inverse of b minus d inverse of L plus u times x. Now this is a constant term, okay? And this is xn plus 1 is equal to xn. Now if you find the error, you will if you are trying to calculate the error to try to find the convergence, you will find that this is your convergence matrix. So this matrix will give you the convergence criteria. That is minus d inverse of L plus u. This is for Jacobi. And for Gauss-Seidel method, GS, this matrix will be H equal to minus of B plus L inverse. Just use the idea of the algorithm, how it is developed. Then it will find this is very trivial. So this matrix will give you the convergence criteria. The same procedure like the Jacobi method, exactly same procedure. Only this matrix is different from Jacobi. So it will be D plus L inverse times U. Okay. So this is for the Gauss-Seidel method, GS. Okay. So now for the Jacobi method, so D L U are written over here. Now what is D inverse? D inverse is very easy. D inverse is just half 0 0 half. Yeah. Now and what is L plus U? L plus U is 0 minus 1 minus 1 0. Now you need now you need for these matrices you need to find its eigenvalue, and you need to find the maximum of the eigenvalue. If it is less than 1, then the solution will converge. Then the then the then this iterative procedure will converge. If it is greater than 1, then the iterative procedure will not converge. Okay. So I will now here I will do it by hand for the Jacobi method. Later I will show in code both for Jacobi and the Gauss-Seidel method. Okay. So this is L plus U. So I just need to calculate D inverse L plus U. So D inverse L plus U, and there is a negative outside. So it will be minus. So let's do the calculation. Minus is outside already. Half 0 0 1. So its first term will be 0. Second term will be minus of half. The third term will be 0 minus half and 0. So it is 0 half half 0. Now we you need to so yeah, so I have taken, so I have included the minus, so negative sign, so it will be 0 half half 0. So what is the eigenvalue? If you calculate the eigenvalue, if you find it will be plus minus of half. Okay. And the maximum eigenvalue half, it is less than 1. Okay. So for the Jacobi method, this solution converges. So later I will show. Again. So I am telling again. So for the Gauss-Seidel method, that we will find that the solution converges as well, and I will show that in the code. Now let's move to the next question. That this is question number 10, which says that for the incursion symmetric and positive definite matrix, the diagonal elements are positive, negative, can't say. Okay. So uh, you need to you need to go back to the definition of the positive definite matrix. The one condition was that positive definite matrix is such that whose eigenvalues are all greater than 0. So lambda 1, lambda 2, lambda 3 all are greater than 0. Okay. And it says that the diagonal elements, and also you can find, so you can do it in the opposite manner. Like if you want to find a pivot, okay, this is a square matrix. This is a square matrix, so obviously the pivot elements will be the most probably diagonal elements. Okay. And you need and if you want to be at a positive definite matrix, then all those pivot elements should be greater than 0. So all diagonal elements should be greater than 0. So this should be the correct answer. So this is the correct answer A, positive definite. Also, you can go and you can also consider a problem from the eigenvalue points of view. So you can find that define the trace, that the trace of a matrix with lambda 1, lambda 2 plus lambda 3 equal to sum of the diagonal element dii. So you can also argue from that point of view. Okay. Now here you here this is the so this is again a problem on the positive definite matrix, that for a positive, here you need to prove that for a symmetric and a positive definite matrix, the eigenvalues are all positive. Okay, you need to prove that here. So x transpose a x is greater than 0. This is a very easy proof. Okay, I so x transpose a x is greater than 0 for this matrix. Now Ax equal to lambda x. Yeah. So this implies x transpose lambda x is greater than 0, means again lambda is just a value. So I can easily do this. There is no problem in that. If lambda is a matrix, then I can't do that. Okay, because lambda is a value, so I can just take it outside and operate on this two. This is greater than 0. This implies lambda norm of x square is greater than 0. So this is a positive quantity. Okay, this is just a distance, so distance square. So this is a positive quantity always. And here this is symmetric matrix. Okay, so that means all eigenvalues are real. So on the possibilities lambda greater than 0. So this is a very easy proof that for a symmetric and positive definite matrix, all eigenvalues will be greater than 0. Right. Yeah. So this is So this is another problem. Okay. After this problem, we will move to coding. So this is a matrix. So 1 minus 1 0 2 7 2 0.5 0.3 0.9. This is the matrix, and you need to find LD and U. Very easy problem. So later I will show how to find L, because in reality you will not get the 3 cos 3 matrix. You will get probably 1000 cos 1000 matrix, and you need to operate with that. There you cannot just look at the matrix and find what is D, what is L, and what is U. There you have to code. You need to use Matlab to find that. Okay. So I will show a code where you can find, and I will also say share it with you, where you can find this LDNU from the given matrix. So here, just by looking at it, we can simply say what will be D. D will be 1 0 0 0 7 0 0 0 0.9. So this is your D matrix. What will be U? What will be L? L will be everything below the diagonal. That means 0 0 0. First 0 0 0, ah, ah, sorry, it will be 0 0 0. Okay, this will be 2 0 0 0.5 0.3 0. What will be U? U will be everything above diagonal. Okay, below that it is 0. The first is 0, it is minus 1 0 0 7, no, not 7, 0 2, and 0 0 0. So this is U. Okay. So just by looking at it, you can find what is D, what is L, and what is U. Now we will move to the coding part. Okay, so before that, I think let me just solve this problem completely. So we have the expression for U. Now you just need to find out what is L, and you can find it very easily just by multiplying these numbers. Okay, E21 inverse, E31 inverse, E32 inverse. Probably I can also deal with a similar kind of problem as well, so that you will understand this LU decompositions better. So let's first solve the problem completely. Then I will solve a similar kind of another problem. Okay. All right. So I need to take this E21, E31, and E32 matrix, and I need to multiply that. Okay. So what is E21 matrix? E21. So this is question one continued. Just a second. Let me just save the recording, and I will continue again. Let me just save the recording. Just a moment. Okay. Now let's continue with this calculation. So my E21 is equal to 100 half 10001. I will first write this E21, E31, and E32. Then I will find L. In finding inverse is very easy. I just need to change the sign of the off diagonal elements. So it is the E31 is E31 is okay. So the octagonal element is 1 by 4. So 1 0 0 0 1 0 1 by 4 0 1 and E32, it is probably 11 by 10 the octagonal element. So but again let's be sure, yeah, it is 11 by 10. It is 1 0 0 0 1 0 0 11 by 10 and 1. Now I need to inverse it and multiply it. So I am writing it directly. So let's just be sure about the multiplication order, because if I change the order, then the final result will be completely different. So E21 inverse, E31 inverse, E32 inverse. So this is the order. So first let's solve. E21 inverse is 1 0 0 minus half 1 0 0 0 1 into 1 0 0 0 1 0 minus 1 by 4 0 1 into 1 0 0 0 1 0 0 11 by 10 1. Okay. Sorry, it will be minus 11 by 10, right? Now here is a small trick. Okay, the final result, it you can so you can after let me write the final result, then you will be able to see the what is the trick. So first element in all these three matrices, it is 1 0 0 0 0. I am writing the final result. This is L. Okay, and here it comes minus half. The second element is same for all, 1. Third element is also 0. Now this 3 1 position, it will come minus 1 by 4. Hmm? Now here I will write minus 11 by 10, and this third element is 1. So you see what has happened. So this is the trick. You don't need to really multiply everything. Just just put this in the according places. Okay, and you will be able to get the result. We can verify it now. So first let's multiply these two matrices. 1 0 0 minus half 1 0 0 0 1 into 1 0 0 0 1 0 minus 1 by 4 0 1. Let's multiply. First row first column is 1, first row second column 0, first row third column 0. So this is minus half 0 0 0. So minus half, this is 1 0. So this will appear as 0. No, not 0, sorry. It will appear as minus 1 by 4. It is appear as 0 0 0 0 and 1. And I need to multiply 1 0 0 minus half 1 0 minus 1 by 4 0 1 with this matrix 1 0 0 0 1 0 0 minus 11 by 10 1. Let's do the multiplication. It will first element will be 1, this will be 0, this will be 0. So this will be minus 1 by half. Mhm. 0 1 1. This element will be 0. This will be minus 1 by 4 0 0. This is minus 11 by 10, and this is 1. So you see that these results and these results are the same. So you don't need to really multiply. So you don't need to really multiply these things. Okay, you can you will be you just put those numbers in their according places, and you will get the solution. Okay. So okay, so now let me so now I will start discussing about the codes. So if I have time at the end, then I will again solve another problem on this LU decomposition. So let's move on with code right now. Yeah, this screen is not visible. Yeah, so this screen is visible now. uh, okay, so the first question, suppose you are given a matrix. This is your matrix. M equal to 1, 2. Yeah, I think so. I think I will show you. I will. I will do the LU decomposition on this matrix. Okay, then it will. You will be able to understand very easy. So what is the so this the LU decomposition, the inbuilt LU decomposition that Matlab uses, it is not exactly the LU decomposition that we do by our hand. They do a PLU decomposition. Okay, they additionally add a permutation matrix with L sometimes, not always. This P may appear as an identity matrix as well, I3, but they ge- they're they just generally do PL of U equal to A matrix. Okay, so this so the you so you can see. So first let me show you the code and with a comment for it. So the command is LU, very simple command, LU, for the LU decomposition. Okay, LU of M will give you U and L. You can see that this matrix U, this is there is no problem with this matrix. Okay, this is 780. So this is the upper triangular matrix. But if you go to L, you will see that this is not exactly a lower triangular matrix. Okay, for lower triangular matrix, the below all above diagonal elements should be zero, but here this is not the case, right? Because it has already multiplied a permutation matrix with a P. Because MATLAB does this, MATLAB uses this algorithm. They generally do PLU decomposition, not general LU decomposition. Okay, so if I do normal LU decomposition on this matrix, just a second. So yeah. So if I just do LU decomposition, let's do the LU decomposition of this matrix, the general LU decomposition. I'm using the black color. So 1, 2, 3, 4, 5, 6, 7, 8, 0. So the first step will be R3, sorry, R2 to R2 minus 4R1. Okay, or I can write plus of minus 4R1 because it will be helpful while calculating the E21, E32, and E31. Okay, you will see. So that first step will be 1, 2, 3. This will be 0. This will be minus 3. This is, I think it will be minus 6. And 7, 8, 0. What is your E21? 1, 0, 0, minus 4. B. 1, 0. Because I am multiplying R1 with minus 4 and then subtracting with R2. Okay, and then 0, 0, 1. This will remain the same. Next step will be, I am writing it here, R3 minus plus minus 7 R1. The result will be 1, 2, 3, 0 minus 3 minus 6, 0, and so it will be minus 6 and 0 minus, so it will be minus 21. Okay, So what will be my E31? E31 will be just similar to E21, 100,010 minus 701. So this is my E31. Now I need to operate on these two, R3 and R2. So R3 will be right. So what will be my so the U matrix 1, 2, 3, 0 minus 3 minus 6. Now I have multiplied R2 by minus 2. So it will be plus 6. So 0, 0. So it will be plus 12. It will be minus 9. Okay. Now I have to calculate. So it is your resultant matrix 1, 2, 3, 0 minus 3 minus 6 0 0 minus 9. So similarly, using the same procedure, we will be able to calculate E21 inverse E3 to into E31 inverse into E32 inverse, and you just need to put the signs in their corresponding positions, and you will be able to get the L matrix. But the thing I want to show you, that you see this matrix and this matrix. This is the upper triangular matrix. This is slightly different. This is not same as this matrix, but this is the upper triangular matrix. Okay. So, but if you multiply this, you will finally get your desired result, because Matlab is giving you this result. So it is just to show you this Matlab is using a different kind of algorithm. If you read about it, you will run. So this is not exactly what we are doing over here. Okay. Just when you do this kind of calculation in MATLAB, just keep that in mind. Okay. Now let's go to the second the for so not the second problem. Let's go to the next problem. This is problem number 14. All right. So here I have the consider A and B. A is the governing matrix. That means the which will uh, which is multiplied with x, y, and z. Okay, and B is the right hand side. So A is 50 minus 1, 0, 1, 0, 0, 3 minus 2. B is 2, 2, 4. Now use Gauss-Seidel method to solve this problem, and given that 1, 1, 1 as an initial approximation. Okay. Now if I use that, so what will be the solution of the problem? Okay. Now here I have. So first, I wanted to check about the convergence criteria. Okay, this is not necessary to solve the problem, because it is already said that you need to use Gauss-Seidel approximation. But this is just for clarity. Okay, so this is our matrix: 5, 0, minus 1, 0, 1, 0, 0, minus 3, 2. Just a second. Huh? Okay. So this is your matrix. Now you need to find what is D, what is L, and what is U. Okay. Zeros of n means here n is the length of A, so it will give me 3. Zeros of n means it will give you a matrix of length 3, and it will give you a square matrix. So zeros of n, here n equal to 3, so it will give you 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is the meaning of that. Now now if you want to write a simple vector, you can write like this: zeros of n comma 1. That means it will give you a column. If you write zeros of 1 comma n, it will give you a row. Okay, but let's not go with that, so I am removing this. So this is the meaning of zero. So I have to initialize with something. So I have initialized with that zeros. Okay. So I needed this one. Okay. Now, so for the first one is the simplest one. You need to find D. D is just a diagonal elements of A. So here AII. Okay, AII means this element 5, 1, 1, 2, 2, 3, 3. Now for the lower triangular matrix, not that lower triangular matrix. Lower corresponding to a diagonal. We will not consider a diagonal elements here. So for I equal to 2 to n. Why 2 to n? Because the first one is already 0. So I don't care about that. So I will start from 2. I equal to 2 to n. And j equal to 1 to I minus 1. J is what? J is the number of column. I indicates the row. Okay. So j equal to I to if it goes to I, because there is already an element in I, the diagonal element. So I don't want to go there. I just want to go before that element. Okay. I will just want to go to previous column. So that is 1 to I minus 1, and Lij equal to Aij end, and then I equal to 1 to n minus 1. Okay, now I am starting from here for this 3 cos 3 matrix. So from here I will go from here I am going to n minus 1, because I already know that at I equal to n there is already an element, that is the diagonal element. That's why I'm not going to nth time. Yeah, I am going to the nth row. I am ending my code at n minus 1th row. You can see the similarity between these two. Here I am starting from 2 and going to n. Here I am starting from 1 and going to n minus 1. And here I am starting for I plus 1, because at the I there is already an element. Before I, all those elements are the course are going to the L. So after that ith element, all those elements will go to U. So that's why it will go from I plus 1 to n. And Uij will be equal to A of ij. And end. Yeah. So here I have written A, B, C, A, D, and U. So this is my A. This is D. You can find that this is L. So let's go to A matrix again. 5 0 minus 1 0 1 0 0 3 minus 2. So what will be the diagonal? So what will be the L? What will be the L matrix? Obviously, this will be the L matrix. These diagonal elements are covered. You can see that this is the diagonal elements. On the left is minus 3. What is U? Obviously, this will be the U. All the diagonal elements are 0. Below the diagonal elements, everything is 0. And what I have is 0 and minus 1. So here, this is 0. This is minus 1. Now, the convergence criteria. So what is the matrix? The I have told earlier that in this case, this matrix will tell us about the convergence in case of the Gauss-Seidel method, not in Jacobi. This is for the Gauss-Seidel method. So I have calculated that, and here this I of mat. So I have mentioned about it postally in the first class. This will give you the eigenvalues of this your matrix. Here the name of my matrix is mat. Here, and all the eigenvalues are 0, which is less than 1. So my convergence criteria is satisfied. Now I am here. I have done the main coding part. So where I will try to find the solution to this question. So again I need to write a matrix. This is my matrix A. I am not writing it again because you already know what it is. Yes, n is the length of a same thing. Here I have provided B. B is 2 to 4. Now here this initial condition is provided already 1 1 1, and I have also initiated this xn. Xn is my new my new vector. So the idea is x naught is my old iteration, the result of my old iteration, and xn is the result of my new iteration. So this is the convergence, and this is the tolerance. Okay, this is you can change your tolerance accordingly. So I need to so I need to start so this conf is my the is the counter which measure the error. Okay, so if this conf means convergence is greater than is less than the tolerance, then my loop will stop. Okay, so I have initiated it to value one. Okay, my initial iteration is zero obviously, and the maximum iteration is 50. Now I have started it with this, so I don't want to write anything on the code because otherwise it will be difficult to understand for you. Let me erase these things as well. So this is the condition inside my while loop. If iteration is less than maximum iteration, and if convergence is greater than tolerance, then then the loop will start. Then the loop will work. Okay. So so here I have used for loop. Okay. So if I for I equal to 1 to n, because n is the number of rows and or columns, right? If I equal to 1 for the first row, for the first element, all other elements will come from the previous iteration. Okay, and this is and this is the it will calculate xn of 1. Now for the last element, all other elements will come from the new iteration. Okay, so I have written it there. Now and if I greater than 1 or and I less than n, that means all the intermediate elements. Okay, all the and some of them will come from the corresponding to the lower triangular matrix, some of them will come corresponding to the upper triangular matrix, which indicates that some of the elements will be known, not upper triangular, lower triangular, below diagonal and the above diagonal. This is the correct term. It says the sum of them will come below diagonal, and then those terms are already known to us because xn, and some of them will come above diagonal which are still unknown, that is x0. Okay, x0 from my previous iteration, xn is from the current iteration process. Okay, and after end, and this is the norm. I am taking that norm, this second norm as my convergence. So and after that I have I have updated my value of my x0 and updated the iteration steps. Okay, so here I have printed the solutions and the iteration at each iteration step, and this is the result. At the first step, you get this the answer, and second step, this is the answer, and after third step, you will get that this is the answer. Okay, you are getting just two zeros after decimals because I have written here 0.2f. Okay, and here the below this thing it indicates the iteration steps. I should also erase this so that you will be able to see the solutions as well. Okay, yeah. Okay, so this is the whole coding. So I will solve some more problems on this thing. So there I will also again discuss about the code. Okay, so yeah, so I mean, so what is the correct solution? Correct solution is this one. So this is the correct solution. Okay, okay, just give me 2 minutes. I will come back and again continue. Okay, so let's start again. Now, the same thing. I now we have to solve the problem using Jacobi method. Okay, so this is the matrix. This is the same procedure I have used. Again, I have tested the convergence criteria. Okay, okay, the code is same. Now only the matrix that govern the convergence criteria is different for Jacobi and Gauss setting. Again, I see that the eigenvalue of the matrices is 0, so I can use the Jacobi method to solve the problem. So here everything will, all the rows will come. I mean only, so here we don't update the update values of x in between the steps. After a whole sweep, then we just update the values. This is the basic difference between the Jacobi and Gauss setup. So that's why you will see, you may remember that in one test in the Gauss setup it was xn, but here it is x0, and in case of Gauss setup it was x0, and similarly it is the same here. So in both cases it will be x0 and x0. We are not updating value in between the process. So the both of the code are very similar to each other. Only in case of Gauss-Seidel we use this xn here. Okay, in case of GS, and other steps are exactly the same. Okay, so previously we are getting result at three iteration. Here I am getting at the four iteration steps, and yeah, other things are exactly the same. Only this step, this is little different. Okay, now I'll show some other coding examples. Now, this is an MCQ question. Now, if a symmetric matrix having strictly positive eigenvalues only, then that matrix is known as negative definite matrix, indefinite matrix, strictly positive matrix, positive definite matrix. So, we have already solved many problem on this positive definite matrix. So by this time, we should be clear to you that the answer is the positive definite matrix. Okay. Okay. Now, another coding problem. So, perform two iterations on the Gauss-Seidel method to find the value of x for the following systems of equation. Okay, so this is the your equation. So here it is told in the problem to do two iteration, but we are anyway using Matlab to solve the problem. So I have let Matlab decide how many iterations it wants to go to my desired tolerance 1e minus 4. Okay, and here are four options. So here anything is not mentioned about the initial condition. I have taken arbitrary case. It is 111. The codes are exactly same. But anyway, I will again discuss about it so that this should be clear to you. So at the first step, okay. So x and one. So all the elements will come from the previous iteration x naught. At the last, for the last element, all other elements are already derived. So all those elements will come from xn, not x naught. And the in between elements, these elements will, some of them will come from xn. These are the below diagonal for these are the below diagonal elements, and here some of them will come from the previous iteration. Those are the above diagonal elements. You can see that this is ai 1 to I minus 1, which indicates that this is below diagonal, and here this is above diagonal. Okay, just a second. Yeah, sorry for that. Okay, so these elements, they are below diagonal elements and these are above diagonal elements. Okay, so for the below diagonal elements, we will multiply it with xn, and for the above diagonal element, we will multiply with x naught. And here, this is the convergence. The same, the code is same. I am taking this two norm, and I am updating the value and updating the iteration steps. And we can see that after 6 iteration, I am getting a desired result. Desired result means tolerance. This is below this tolerance. So later in a code, I will show from plotting how iteration step and convergence behave in case of Jacobi and Gauss seidel. I will show that. And here, but here these are the results. And you can see 2.43 here is there. It is the answer. So 2.43 is the correct choice. So now again, so when we are solving using the Gauss seidel, then I have thought that it will be better to use the Jacobi method as well and try to see what it gives. So oh, sorry. So this is so sorry. This is a new problem. Sorry. So this is problem number 18. So I need to solve this initial value problem. Sorry, I need to solve this system of linear equation using Jacobi's method. But observe one thing. So in case of Jacobi's method, you may probably remember that it is better if the matrix is diagonally dominant. Okay, this is not a necessary condition, but this is sufficient condition, which says that if the matrix is diagonally dominant, then obviously you will get a solution. That means your method will converge. Your Jacobi method or iteration method will converge. But but if a matrix is not diagonally dominant, then you may or may not get a converse solution. Okay. So here this is that kind of an example. Here this is, so let me first write down the matrix. 2, 3, 1, 5, 1, 1, 3, 2, 4. You can see that this matrix is not diagonally dominant. Here this is 2, 3 plus 1, 4 is greater than 2. Here it is 1, 5 plus 1, 6 is greater than 1. Here it is 4, 3 plus 2, 5 is greater than 4. So this is not a diagonally dominant matrix. So, but anyway, let's try to find the solution. Okay. Same thing, I have written the matrix. B, this is B, and this is my initial case x0. Okay, and this is xn. It's the same coding, exactly the same thing. So again, that I have mentioned that in this case, unlike the Gauss seidel case, here we do not update the value in between. If here this is x0, this is the below diagonal element, and if the x0 is multiplied with it, these are the above diagonal element. The same x0 is multiplied with that also. Okay, this is the idea. But in case of Gauss seidel, this one should be xn. Okay. So again, the same convergence. I am updating the value and I am printing the results. Let me remove the annotation. Yeah, you can see initially this is minus 2.5, 5. So you can see that after the value, they are growing rapidly, and at the end, you are getting some arbitrary value. This is obviously not the solution for that. So after 50 iteration step, because my convergence, it never meet this criteria. Previously, my solution stopped at 6 iteration because it already met its criteria of tolerance. Here the convergence may be 10 to the power minus 6, which is way less than 10 to the power minus 4, so it converged. Here it did not converge, and as my maximum iteration step is 50, it goes up to the 50 iteration steps. If you take your maximum iteration step 5000, it will continue to the 5000 steps, but you will never get the solutions. Okay. So none of the answers are correct here. So this is just to give you an idea that you can, this is not a diagonal. This is the, again I am telling that this is not a necessary condition. to calculate the convergence criteria, you need to find the D inverse L plus C. You need to find that always. Okay. So here this is just a sufficient condition. You can see that this matrix is not diagonally dominant. So which can give you an idea that which can give you there's some suspicion that this matrix may not be converged. Okay, and from using the Jacobi method, you are seeing that this value is it is growing rapidly, and finally the solution does not converge at all. This is a diverging solution. That's why these values are increasing. Okay. Now, I have done a thorough convergence check of this matrix using D inverse L plus C. Okay. So this is the matrix, length of the matrix. So I am not repeating this again. So these zeros and I have to initialize by something. So this is zeros. Zeros is the easiest option. So I have taken that. Now, where did it go? Yeah. So I hope by this time this is clear to you. Steps. Anyway, I will repeat it once again. So DII is equal to AII. Okay. This matrix is 2, 3, 1, 5, 1, 1, 3, 2, 4. AII. That means A11, A22, A33. A11, A22, A33. It will take D will take all those values and other elements will be 0 because I have initiated with zeros of n. Only this only elements at those positions will be updated. Now for I equal to 2 to n. So I have told earlier because I don't care about the first row because it is anyway the element will be 0 and I will go just up to the below diagonal point. Okay. This is below diagonal point, this is diagonal point, this is above diagonal point. I just want to go to the below diagonal point. So this is the thing. Again, all the other elements will be 0 because I have initiated with 0. So here you can understand why I have initiated with 0. I can take any other matrix for this just for initialization process. But we know that in case of this matrix, the all just all the below diagonal elements will be non-zero, but the diagonal and the above diagonal elements will be 0. That's why I have initiated it with 0. And for u, it will start from one first row, but it will end it will not go to the last row because the last row at the last element will be 0 anyway. So here it will, and here I will just consider the above diagonal element. It will start from I plus 1 and it will go up to n. And here it is uig equal to aig, and exactly the same code like I have mentioned earlier, and I have showed the detail about the code. Here I am repeating it. So this is your matrix A, this is your matrix T. The AL matrix is here, it is correct matrix, it is also correct. Okay, so the code is working fine. Now this is the inverse of this is the convergence matrix. Now I am calculating the eigenvalues of that. You can find that this is greater than 1, this is greater than 1. Okay, so this matrix, so for this reason this the solution did not converge. This is the necessary condition. Okay, not the sufficient condition. So to check the convergence criteria, you may find some matrix where it is not diagonally dominant but the solution converges. Why? Because in that case, your the eigenvalues, all eigenvalues will be less than 1. Okay, you may come across some this matrix, this kind of matrix sometime. Okay, so every time you need to check this criteria, this convergence criteria. All right. Now, okay. Now consider problem 9. Problem 9 is when we have discussed about a problem earlier. So where I have provided you a matrix of 2, -1, -1, 2, and I have told you to, and in that case I have told you to calculate to test the convergence criteria for Gauss seidel and the Jacobi method. Okay, so this is the matrix. Now for b equal to 1 1, now I here you need to find a solution. So this is a simpler problem compared to the all other problems that we have discussed so far. Here your this is your A matrix. N is your length of A, okay, which is 2 here, and this is your B. Okay, so I have taken a difference, so I will edit it here. This is not the B. B equal to B colon 1. Okay, now here I am taking tolerance. Is slightly more accurate tolerance. Okay, 1 e minus 5. Iteration start with 0 and the maximum iteration will finish at 50. Now this is the condition. Again, the code is exactly the same. Okay. Only difference I have made that I previously told you that I will show how the convergence behave with the iteration steps. Okay, and this is the additional, just the addition for that. This comment scatter. Scatter is similar to plot. Okay, but unlike plot, it will give you a point. If you have 2 point and the corresponding xy data, it will give you that point. Okay, so scatter it x coordinate x point it then conv, which is the y coordinate. Here 50 indicates the size of the circle. Scatter by default give you a circle. You can modify it. You modify it by other markers. Circle is a marker. Is 50. This is the size of the circle. And filled. That means the circle you will get finally in the plot. Those will be filled. Okay. So you will see in a moment. So you see it starts from this solution, and finally after 18 iteration step you get the result. Okay, and this is the solution. So I should have written the x axis y axis. This is the it, this is conv. So you can see that it starts from here. Let me use this color. It starts from here. Initially the convergence value is large. Okay, then it gradually decreases. So it is you can say the decrease is almost a kind of exponential kind. And after nine iteration steps, these values are almost zero. Okay, so I could have stopped at this stage, ninth step. Okay, and now I have tested it the same thing for the Gauss Seidel technique. I will not go over the code again. Same code, only this is a 2 cross 2 matrix. Say exactly the same thing. Only the different thing is the scatter thing. Okay. Here you can see, unlike the Gauss Seidel method, sorry, Jacobi method, the convergence occurs just at 5. Previously it was 9, where the convergence becomes 0. It is IT. This is conv. Here it occurring at 5. Now the obvious question is, why is the reason? The Jacobi converges very fast. The Gauss-Seidel converges just after the 5 times step, but Jacobi took 9 iteration step to go to 0. So in order to do that, I did this convergence check. I will not go over code. So this is the matrix was 2 minus 1 minus 1 2. Maybe this time this is a small matrix. So previously I have calculated the eigenvalues for the Jacobi method. Okay, so I have told that I will calculate the eigenvalues for the Jacobi method, and I will show in a code for the Gauss Seidel method. So this is for Jacobi method. Okay, I know that for the Jacobi method the eigenvalues will be plus minus half. We have already solved it. Okay, the eigenvalues are this. Now, if I want to do it for the Gauss Seidel method, let us do here, and we can compare with the code. Okay, so P is 2002, L is 00 minus 1 0, U equal to 0 minus 1 0 0. Now I need to find L plus D first. Yeah, L plus D first, and it will be 2 0 minus 1 2, and I need to find minus L plus D inverse of U. Now what will be the L plus D inverse? So I need to calculate the determinant of the determinant is 4, and it will be 2, the sign change. So what was the formula for that? 2 0. Right. Oh, okay. So I think this will be the result. I hope this is correct, but let's just verify. So L plus D inverse and L plus D should give you an identity matrix. Okay. So 1 by 4, 2 0 1 2, 2 0 minus 1 2. It will give you shit, 1 by 4. So 4 0 0 0 4. So it is 1001. So this answer is correct. Okay. So L plus D inverse is equal to half 0 1 over 4 half. Now I need to calculate minus L plus D inverse times U. Now what is your U? 0 minus 1 0 0. So multiplying with 0 minus 1 0 0. So what will be the final result? First row first column is 0, first row second column is minus half, second row first column is 0, second row second column is minus 1 by 4. Now I need to calculate the eigenvalues. Okay, so this is an upper triangular matrix. So eigenvalues will be lambda equal to 0 and minus 1 by 4. Now let's go to the code and verify it. This is your A, N is there. Yeah, so Uij, right? LD. So inverse of B plus L star U. So it is giving a find a matrix, and it is giving you 0 and 1 by 4. Okay. So this one, so previously the here the maximum eigenvalue is 1 by 4, and the previously the maximum eigenvalue was half. So you can so in this way you can also argue that as this is as the for the maximum eigenvalue is so spectral radius for Jacobi is greater than spectral radius for Gauss-Seidel. Spectral radius I have mentioned earlier is the maximum lambda. Okay, as this is greater than this Gauss-Seidel, so it converges slower. So this is the reason for this kind of plot. It is converging. It is converging at the ninth iteration step. The value, the result is approximately 0 here. But in case of Gauss Seidel, the procedure is very fast. The result, you are getting the result after the fifth iteration step. The conversion is nearly 0 around that point. Okay, so that's all that I wanted to cover for today's class. Just for a brief recap. So we have solved some many problems, many problems on the positive definite matrix. I will share all these documents with you. Yeah, so this rough calculations will remain here, but I will just make it sure that I do not overwrite anything on the code itself. Otherwise, it will be difficult for you to understand it. So just before finish today's discussion, I will just briefly go over the Jacobi and the Gauss-Seidel code, so that there is no confusion about it. phone. I should- Yeah, I think this is clear. So there are three main codes. One is finding, right? Okay. So first one is the finding DL and U. Okay. So please verify if this is working fine for some 5 plus 4 5 matrix, 6 for 6 matrix. Okay. You will find a comment. You don't need to put this value manually. There is a command called rand. Okay, so if you put some rand 7 or 8, it will generate a 7 cross 7, 8 cross 8 matrix with some random number. All those numbers will vary between 0 and 1, and you use that thing rand, okay, and verify this code for finding DL and U. Okay, finding DL and U is necessary. Hello. So finding this DL and U is necessary. So I will just write it here. Rand for checking the convergence criteria. So here this this loop is for calculating L. I am starting with 2 because already at I equal to 1 the diagonal element is sitting there, it is already 0, so I don't need to start from there. And here here for the J I defines the row, so I should probably mention it here. I row J column. So, and the column will start from the first column, and it will go the below diagonal column. I mean to the left column before the diagonal. And this is Lij equal to Aij. You are substituting. You are just exchanging the value. And similarly for U, it will start from the first row, but it will finish just before the last row, because at the last a diagonal element is sitting there. And here I will start from I plus 1. It is the right side of the diagonal, and go to the last column. And here I am substituting the value of U. I am substituting U and A, exchanging the values. Okay, and you will see that this is the final result for that. So this is the programming for DL and U. And I will briefly again recap about Gauss seidel and the Jacobi iteration.
अच्छा लो ना बेटा.
So this is for yeah. So this is for the Gauss seidel iteration. Here initially I am defining the matrix, the convergence, the tolerance, those basic things you need to define for your matrix. Be sure about the dimension, what kind of dimension you are taking. Okay, don't if you are using if you are using column vector as your initial vector, please be sure that you use your new vector accordingly. If you are using a column vector as your initial guess, and your new result as a row vector, then MATLAB will show you error. Okay, just be consistent with the dimension. So this is for I equal to 1. Okay, this is for the I equal to n. For I equal to 1, all the unknowns, all the x that we are trying to find will come from the previous iteration step. In case for the last row, all those x will be x new, because all those values we have updated already. And for the all the intermediate steps, intermediate variable, we will use some mixture of xn and x naught. Okay, so I have already mentioned where we have to use the xn and where I have to use x naught. And in case of the Jacobi iteration process, we don't need to bother about this I equal to 1, I equal to n, anything. this just replace in place of xn with x naught in case of the Jacobi iteration process. Okay, so here in the Gauss level iteration process, as we are updating our value during the iteration step, so this is much faster, which you can again anyway argue from here. I have shown in the last example, which and you can anyway argue from the using the convergence matrix. You can see that here this matrix is eigenvalue is 1.1 by 4. Here this eigenvalue is 1 by 2. So this 1 by 2 will converge lower than the 1 by 4. And for the last that and the so this and the diagonal dominance here in this example, I have shown that the diagonal dominance is a sufficient condition. So if this matrix is not diagonal, if this matrix is diagonally dominant, then Jacobi iteration will definitely work. But if it is not diagonally dominant, then you can you can be sure if it is if it will work or not. You need to check the convergence criteria. So I have used Jacobi iteration technique, Jacobi method to solve the problem, and we have seen that after 50th iteration stage, the solution just blow up. It didn't converge. And again, at the last, for this matrix, I have calculated. Sorry, I have calculated the D, L, and U, and I have checked the eigenvalues. And here we have seen that this eigenvalue is greater than 0. This is the modulus of this eigenvalue is greater than 0, and this is also greater than 0. This solution did not converge. Okay, so I will stop here, and I will share this I will share the upload my recording in my channel and share those notes. Okay, so good night, and we will meet again in the next week.